right, here we go. All right, so we are going to continue. Last class we did not finish integration by parts, right? So we are going to continue that today. The problem that we did, I'm not sure if this was the order we did it, but I think this may have been the last problem that we did right here. And so we still needed to do this one, and then there's one more after that. So for this one, I'm kind of giving it away here, but let's just look at it from like, you know, like a clean slate. Let's act like we weren't given any prompting on this. Let's just go through it and make sure we understand why integration by parts straight away doesn't seem to get us anywhere. So if you try integration by parts, what are you going to choose for your u, and what are you going to choose for your dv, right? That's kind of where you are at the beginning of integration by parts every time, right? So you don't have many choices, do you? Right? I mean, what could you do for u? E to the root x, you could do that, right? E to the root x, and then that would force this to be the dx, right? Now you could integrate that, and then you could differentiate that, but you're going to have like chain rule going on here, aren't you? You're going to have to do derivative of this is itself, then times derivative of the square root, which is going to give you something. And so I think, you know, maybe you could try that, right? Do you see any other way I could set this up? Like, well, yeah, but I'm saying let's act like we don't know that. I'm trying to say, why is it that we're going to try a basic u sub first? Off of this, we don't seem like we're. Do y'all understand? Like, it's not going to be pretty when we take derivative of this. I mean, maybe it'll work, but let's.
Steps that you could mess up very easily.
Yeah, I mean, it just may look ugly. It may be doable. All right. So this one says, look, you always want to pay attention to the fact that you could make a u substitution first. But what's like the general rule with u sub? Look for something in there and its derivative must be there, right? Well, that's a problem because I'm looking and I'm not seeing something and its derivative. But we have seen problems in the past with u sub where even though we don't see something in its derivative, we still can make a u sub and it might work, right? So this is where that persistence comes in. So we're going to make a u sub here, even though it doesn't look like a u sub is going to do anything. And we're going to make the u sub of square root of x. Now that may seem like, okay, look, I need the derivative of that somewhere, right? For u sub, and I don't see the derivative of this anywhere. Like if that's u, right, then where's its derivative? It's not there, right? Okay, well, let's just carry on. The derivative of this will be 1 over 2 root x. Have I done that enough now? That everyone's okay with this? Okay, so we're sitting there, we're like, wait, you know, like where is that, right? It's not there, okay? However, what we realize here is that this right here, okay, that really is what? That's really u, isn't it? I mean, that's what we called u, yes? Okay, so I could rewrite this as du equals 1 over 2u dx. And it's still, it doesn't look like I have this, but let's just do some algebra here. Let's move the 2u to the other side. And what we come up with is something that we can replace dx with. You see that? I can replace dx with this expression, and this expression has u in it, right? U and du. And I'm already going to replace this square root of x with the u, so I should be able to convert the entire integral over to things with u only, right? So it's this, the key to the problem is realizing that this right here can be swapped out for that. And now we're just going to rewrite it. So this integral becomes, well, we know this is e to the u, right? And then the dx becomes 2u du. I'll just put it here, 2u du. And then I'll pull the 2 out. 2 integral. And then I'm just going to like rearrange it. I'm going to put the u in front, and then e to the u after that, and then du. That looks a little bit more like the way we've seen these before. Okay, any questions on that u sub? Okay, so now here, When we look at this, this looks more like an integration by parts problem. It's very much like the first quiz problem, isn't it? It's kind of like you have x e to the x. So if we let our u be x, right, then it should work. The problem is I've already used the variable u, haven't I? So I can't use u again. So what I'm going to do is I'm going to create my table for integration by parts now. I'm supposed to put u here and dv here. But instead of, I can't use u, so I'm going to use a different variable. Any variable I want, I'm just going to go with w, all right? So I'm going to call this w is going to be the u, and then what's my dv going to be? E to the u du. All right, so now I can still set this table up, just using different letters, still going to differentiate down, integrate up, and then I'm not going to have ultraviolet minus voodoo anymore, right? It's different letters, but the same process. It'll be this times this minus the integral of this times this. So let's see. You know, I'm not separating these sticks every time, so I'm sorry if you already got called on last class. You may get called on again. Where's Luke at? Luke? Okay, Luke. I feel like I called you last time. Can you complete this table for me?
Yeah.
dw is 1. We'll call it 1 du. How about that? Okay, and then here, what's there? E to the u. All right, everyone agree? All right, so now this integral becomes 2. Let's see, 2 is going to stay there, right? Because it's being multiplied outside. And now I start the formula, ultraviolet minus voodoo, but we don't have ultraviolet, right? So I'm going to put a bracket, and then let's see. Adam, where's Adam at?
Right.
Okay, Adam, can you tell me what I need to write next?
So instead of u, it'd be w, so you just put there as u times e to the u,
Times e to the u
and then
minus
integral
integral
e to the u
uh-huh,
times
du. Okay, just like that. And Adam, that seems like a doable integral, right? That's pretty straightforward. So we can just take the antiderivative of this. We're just going to get e to the u. And then we'll have a constant. So I think I can squeeze it all in here. 2u e to the u minus e to the u plus c. Oh, I put my bracket, sorry. Bracket. I have to have that to distribute. Thank you. And notice, again, I didn't care about the 2 on the c. It's still a constant. Last step. Get u back to the variable that we started with, which was x, right? So what was u? We go back when we made our u substitution. U was the square root of x, wasn't it? So our final result is 2 bracket, let's see, square root of x, e to the square root of x, minus e to the square root of x, and plus c. We could distribute the 2 through if we wanted to. We could also factor an e to the root x out if we wanted to, but algebraically we're good. Like we're at the answer. Okay, any questions? Yes?
Why, when you integrated e to the u,
Mm-hmm.
you still made it just e to the u when u is the square root of x? Shouldn't it be multiplied by 1 over u?
1 over u. You mean out front here?
Yes.
Okay, u is a variable, not a constant. So look at it this way. Look at it this way. There's really a 1 in front of that. So we do scale it by the constant in front, but the thing is it's 1 over 1. So like had this been 2u, right? Then we would have had to have put a 1/2 in front. But we wouldn't have put a 1 over u, right? Does that make sense or not? You sure? Okay. Another way you can look at it is this way. This is what we were talking about earlier. So if you do this and you scale by 1 over u, the reason why that's not going to work is think about the idea here is that if you take the antiderivative here, you get that, right? So if you take derivative of that, you should get this. Problem there, you have product rule. So this would be a very complicated derivative. It wouldn't turn out to be this. Make sense? Okay. All right. So that is an example of doing a U substitution first. That U substitution didn't even look very natural, like it would work, but it did, right? So we're just kind of adding layers onto this, aren't we? Like, again, this is nothing is cookie cutter. Everything is, you got to try something, maybe it'll work. Crumble up your paper, try again. Are y'all okay? Y'all seem a little bit bummed out today. Are y'all all right? Sure? Is the Super Bowl wear you out or what?
Just tired.
Yeah, just tired.
Would it be more pertinent to factor out 2e to the...
Would it be, but algebraically, they'd be the same answer, right? So unless we're going to do something with that antiderivative, like set it equal to 0 or something, like you wouldn't need to factor it. You know, if you're looking in the back of the book, they may have factored out the e to the root x. But it's not any more correct, right? It's still the same expression. All right, so the next example is really, I think, a very interesting one. So if you go and you look in the back of the book, if you have the book, if you have a used one, you probably won't see this, but you know, I gave you the formula sheets, right? You're allowed to use those on the test. And if you look at reference page on your formula sheets, reference page 6, which should be the last page, you'll see that you have all these antiderivative formulas here for you, right? These are all here. And it goes all the way through, what, 29? There are 29 formulas on here. But it turns out that if you have the original book, there's like another couple of pages of formulas, all right? And I don't give you those, so you're not allowed to use those. And they're actually like entire books full of just integral formulas, things that come up, and so an engineer can just flip to it and just go get the formula without having to do any techniques. And even today, that's obsolete because you have like Wolfram Alpha, and you just go there, type the integral in, and it spits out the answer, right? So these tables are kind of like not necessary anymore. But there is a formula on here that you can't see, all right? It's formula number 73, and this is the formula. Okay, it's the integral of sine to the nth power, right? The integral of sine to the nth power of u du is equal to negative 1 over n sine to the n minus 1 of u times cosine u plus n minus 1 over n times the integral of sine to the n minus 2 of u du. Whoa, right? Okay, so we want to show that, like we want to actually generate this formula ourselves. But I want you to just first look at it and try and understand what's happening here. Okay? So I'm going to give you an example of how you could use this formula. If we were trying to do the antiderivative of sine to the 10th power of x dx, let's say we were trying to do that. Would this formula be acceptable? Yes, okay? So what we would do is we would say, okay, according to the formula, this is, bless you, this is going to be negative 1 over what? So for us, n is 10, right? This is our n. So this should be negative 1 over 10 sine to the 10 minus 1, so that's 9th power of x, right? Because we're using x instead of u, times cosine x plus 9 over 10 integral of sine to the 8th power x dx. Okay? With me? So the antiderivative of sine to the nth power, it's the 10th power of this, is this plus this new integral, right? So now we have to do this integral. How can you do this integral? Use the same formula again, right? So what our next line would be is this. Negative 1/10 sine to the 9th of x cosine x plus 9/10, and now a bracket. And now we use that formula again, but we use it on this piece right here instead, right? So now what's n? N is 8, right? So our formula is going to be negative 1 over 8 sine to the 7th x cosine x plus 7 over 8 integral sine to the 6x dx, right? And then we close that off. And now what? we got to do it again, right?
Going all the way down.
And what we do is we keep reducing the power, right? Each time we do this, the power on sine keeps coming down by 2. And eventually it's gone, right? So what a formula like this does is it allows us to take a sine to a power and rewrite it where we are reducing the power each time we use the formula, right? And so we call these reduction formulas. See? So I'm about to show you how to create the formula, but this is called a reduction formula, all right? And in the back of the book, there's a bunch of them. They have this for like cosine to the n and tangent to the n. So I'm just going to show you how to create this reduction formula, all right? You ready? Here it comes. That's how it's used. I'll never give you a problem like that. I'll never ask you to use this formula. I just want you to see how the formula is generated, because these formulas were created by human beings, right? Like, we didn't just like find some tablet full of math formulas somewhere, right? It's like every one of these we had to make, right? So let's start with the original problem. All right, so here we go. I'm going to use x instead of u. Is that all right? X instead of u? All right, so the hint here is that we're going to use integration by parts. Okay, that's the hint. And I think if you look at the formula, it's kind of cheating, okay? But if you look at the formula, you can kind of tell what your u and dv need to be, because this is the first part here is ultraviolet, isn't it? So if this is ultraviolet, think about the table. The table's got to be, u, and then here's our dv. We know that this up here, right, whatever v is, these two multiplied have to be these two, right? So the question is, like, which one goes where? So we are going to maybe, how about this? If we do, would you agree that this and like that looks kind of like what our table should look like according to this, right? Do y'all kind of see that? Okay. Now, we still need to do our u and dv. I was just trying to get you to see, like, we can use the formula to kind of help us. If you didn't have this, imagine you didn't have that formula right there. Imagine this wasn't given to you and you were just like sitting there trying to figure this out for the first time, right? This would be very difficult to do. So here's the key step, all right? And please understand, I do not expect that anyone in here would get this on their own. Like, just if I gave it to you, just like miraculously come up with the formula on your own. So you have to understand somebody spent a lot of time trying to figure this out, all right? And I'm just going to show you, look, this is really cool what they did and it works. So what they did first is this. They split that up. Is that still sine raised to the nth power? So look at it this way. If you had sine to the 10th x dx, could you rewrite that as sine to the 9th x times sine x? Yeah, that's the same thing, right? That's sine times sine 9 times, and this is times sine. So that's really sine to the 10th, right? So if we have sine to the nth, we can write it as sine to the n minus 1 of x times sine of x. Agree? And now let's just come and make our table. And let's let our u be the sine to the n minus 1 of x. And that means our dv has to be the other piece over there, which is sine x dx, right? And now let's just carry out the integration by parts. So let's go up first. This one's a little easier. What is v, Alex? Where's Alex? Okay, so what's v? This one's the easier of the two. Negative cosine x, right? That's it. Right? Everyone agree? Okay. Let's see. How about Charles? Where's Charles? Charles? You get the harder one. You have to differentiate that. So what would the derivative of this be? And just think about, like, if you need to in your mind, like, imagine that sine to the 9th x. Like, how would you differentiate that? Bring the 9 down, right? But for us, it's not 9. It's what? n minus 1. So I'm going to bring that down, n minus 1. And then sine to what power? So if it was 9, it would now be what? 8. So if it's n minus 1, you need to take another 1 away, right? N minus 2. Okay, n minus 2 of x, right? Okay, so you've done this part. You've taken the 9 out, did sine to the 8th power, but now chain rule, what do you still have tacked out here on the side? Cosine x, right? And then dx, right? That's what we would have. Now you can start to see that in this table we're starting to get pieces in here that look like our formula, right? You see how we have the sine to the n minus 2? See that? Like it's in here, isn't it? And that's part of the voodoo, so it makes sense that that's going to be there. Okay, any questions? I'm going to rewrite everything now. So this now becomes, no more integral sign, right? We're going to do ultraviolet. Yes?
Yes, sir.
So it's going to be this times this, right? So I'm going to have negative sine to the n minus 1 of x times cosine of x. Okay, minus, I'm going to leave a little space here, integral, and now I need to do voodoo, right? These two multiplied. So this has a negative on it, right? Which is going to make our minus become a plus. Are there any constants that I can pull out of these two? Constants. The n minus 1, right? The n minus 1 is just a number. Like it was the 9 that you pulled out earlier, right? So that can come out of the integral and the negative can come out. So I should have a plus n minus 1 here, right? Plus n minus 1. And then inside the integral, I still have sine to the n minus 2 of x times cosine x again. Agree? Yeah? Okay, so we have sine to the n minus 2 of x times cosine x dx. All right. Is that all right? The negative is already out. The n minus 1's already out. So now we have to work with that. Is that kind of starting to look like the formula? A little bit? I mean, we've got the sine n minus 2 of u. We're using x, right? We have that, dx, but we don't have a cosine squared, do we? We don't have that in here. We have an n minus 1 on the outside. We have an n minus 1. That's good. I don't have this n, and I don't have that n, do I? I don't have either one of those. Okay, so there's more work to do. All right? So now what we're going to do is not yet. We're going to put these two together to make that a cosine squared x. And then we're going to use a Pythagorean identity. Remember our Pythagorean identity? Well, I hope you do. I would be disappointed if you don't remember this identity. That one right there. So we agree that from that identity you can solve for cosine squared and you get 1 minus sine squared, right? So what I'm going to do is I'm going to replace this with 1 minus sine squared. Okay, and that'll be my next line. So here's where we are. Watch the way I write this. The original problem, right? This is our original problem, is equal to negative sine to the n minus 1 of x times cosine x. That's our ultraviolet. And then we have plus n minus 1 integral sine to the n minus 2 of x times, now I'm replacing this, right, with 1 minus sine squared x, so I have to put it in parentheses, right? It must be in parentheses. And now let's just distribute this sine to the n minus 2 of x. Let's just distribute it through, all right? And let's see what happens. It's a lot of writing, but it'll be worth it in the end. All right, so we have sine to the n minus 2 of x dx. Okay, let me see. Well, you know what? I'm not going to do that. And then, all right, so that's just here to here, right? So where's Juan? Juan? So Juan, are you with me?
Kind of.
Okay, so I'm distributing this through, right? So this times 1 is itself, okay? What would this times this be, though? So they have the same base, right? The base is sine x. So different exponents, you
Multiply.
add. Add them. So what's n minus 2 plus 2?
That's 2. And
Just n, right? So we're going to have here minus sine to the n of x, like that, dx. We still on board? Now, we have two terms, right? When you integrate, you can do them separately, one at a time. So that means I can do this integral and then this integral separately. So what I'm going to do now is I'm going to split this into two integrals, and keep in mind that the n minus 1 has to come with us. So my next line will be sine to the n of x dx equals negative sine to the n minus 1 of x times cosine x plus n minus 1 times the integral sine to the n minus 1 of x dx minus n minus 1 times the integral of sine to the n of x dx. Let's just make sure I got that right. I split this into two integrals, right? This one and this one. But the n minus 1, what am I missing? Oh, this one right here. Yes, thank you. N minus 2. 2. There we go. So this one here and this one here, right? But the n minus 1 is in front of both. Does anyone see it? What now? Yeah, see, look. This right here is this original integral, isn't it? We had this happen last class with one of the problems. I said this is really kind of a special problem because the integral you're looking for appears on the other side. So if we wanted to move this whole thing to the other side, I would have to add to both sides what? Add n minus 1 of these integrals to this side, and then add n minus 1 of these integrals to this side. And then it'll go away over here, right? It'll go away over here. And how many of these integrals do we now have? We have one of them, right? We have one of these apples, and we're adding to it n minus 1 apples. So how many apples do we have total? If I have n minus 1 apples and I add one more apple, I'll just have n, just n apples, right? So you're just adding the coefficients. N minus 1 plus 1, so we should have n of these integrals, shouldn't we? Okay, so yeah, I'll just do it here. Here's where we are. So we have n of these integrals is equal to negative sine to the n minus 1 of x times cosine x. Okay, that's this part. And then we have, this is still here, plus n minus 1 integral of sine to the n minus 2 of x dx. That's where we are, right? And last step, divide everything by n. So if I divide this term by n, this term right here, this term right here by n, I get the negative 1 over n, don't I? And if I divide this right here, this whole thing by n, that's where I get the n minus 1 over n. So we're there. It's kind of interesting, yes? All right, so that was just more like, hey, isn't that like kind of cool how we can create a reduction formula just using integration by parts? Like, that's interesting. Well, it's interesting to some people, right? Others are just like, give me the formula.
Like from 37 on.
Is 37 a reduction? I think it might be. I don't recall. Yeah. Okay, so that's it for integration by parts. All right, we are done. And you should be able to complete everything there. Were there any questions over anything on the homework? Any of the problems? Or anything else? We're going to get into 6.2 now, if you don't have anything for me. Let me plug my laptop in. All right, let me tell you about the next section, 6.2. 6.2 has two different concepts in it. Trig integrals is the first concept, and the second concept is trigonometric substitutions. So let me bring up my little notes here. Where the heck is it? I had it. There it is. All right. So we are going to be doing two separate topics, trigonometric integrals and substitutions. So it's actually trig integrals, and then the other part is trig substitutions. Today is just trig integrals. You cannot do trig substitution unless you have become proficient with trig integrals, right? So you have to be good at trig integrals to have any hope of doing this, all right? So here are some things we already know. We all know the antiderivative of sine is negative cosine. We all know the antiderivative of cosine is sine. We also know that if we had a constant, we talked about this last class, if we had a constant in front of x, we just have to kind of scale it out, right? So we've done enough of that. After that, there's just kind of a general strategy on how to do these things, and I will get through the strategies. I will explain these to you as we go through some examples. The first problems we're going to look at are just integrals involving sine and cosine. All right? If we see sine and cosine in an integral, here's how we're going to attack them. All right? And to do this, we must be comfortable with the Pythagorean identity, which is the sine squared x plus cosine squared x equals 1. We also have to be comfortable with, remember these identities from pre-cal? These are called the half-angle identities or the power-reducing formulas. So I'm going to put these up on the board on the side because I'm going to need them, but they are all in your formula sheets. In this page, there's a page on your the file, you know the files you can print out and bring? One of them says trig substitutions on it. Who has that in front of them?
Trig substitution.
Yeah. No one has it? You don't have it there? It's not with the, it was a separate file. No? Yep, there it is. Yep, can I see that? You don't need to take it out of there. Okay, so this page is on your, in our Canvas files, and you're allowed to use this on the tests. Now, it doesn't tell you like everything you need to know, but the strategies that I have here are all here. And it also gives you some of the identities that you need to, in case you forget them, all right? But for today, I will put the main identities we're going to use. Sine squared x plus cosine squared x equals 1. Remember that that's the same as cosine squared x equals 1 minus sine squared x. And we can also write that sine squared x equals 1 minus cosine squared x. All those are equivalent, right? And then we have the power-reducing formulas that say sine squared x equals, you may have seen it this way, 1 minus cosine 2x over 2. And then we have another one, cosine squared x equals 1 plus cosine 2x over 2. Those two are from pre-cal. Well, they're all from pre-cal. But these two right here, these two sometimes don't appear on formula sheets. That's why I give them to you on that one sheet. When you see me use these two formulas, I'm actually going to write them a different way. I'm going to take this 2 out the front. It's going to look like this. 1/2 1 minus cosine 2x. And the other one is 1/2 1 plus cosine 2x. It's the same expression. It's just I pull the constant out to the front. All right? We need all those formulas to do what we're about to do. Any questions on that? Okay, here we go. First example. Sine cubed 4t dt. Sine cubed 4t dt. Sine cubed of 4t dt. So we're using t instead of x. All right, so this is a trigonometric integral. It has trig function in it, right? Sine. Now, could we use the reduction formula we just We just did. We could actually, but we're not going to, all right? We're going to do this using some sort of method. And the reason why is because the reduction formula only works if we have sine here. If we mix sines and cosines together, you can't use the reduction formula. So we need more of a method in place. So what we do first, I will bring up that formula sheet. There we go. So let's go up and look at this. Okay, it says, all right, if you've got sines and cosines, if you have cosine raised to an odd power, do we have that? No, okay. If we have sine raised to an odd power, do we have that? Yes. We do. Then what do? Okay, it says we are going to factor out a single sine, factor out a single sine, which leaves us an even power of sine, and then we're going to rewrite that even power using this Pythagorean identity. Okay, that's it in words. Let me show you that in action. So we have sine to an odd power. We are going to factor out a single factor of sine, which means I'm going to rewrite this as sine squared 4t times sine 4t. You all agree that's the same? Okay, now we should be left, because we start out with an odd power of sine, we should be left with an even power of sine, which we have, right? That even power of sine, we are going to use this Pythagorean identity to rewrite it. So when we rewrite that, it should become what here? What does this become? In parentheses, right? 1 minus cosine squared of 4t, close the parentheses. That's sine squared of 4t rewritten in terms of cosine. And then we still have next to it what? Times sine 4t dt. Okay. Does that make sense?
Yes.
Now, why do we do that? That's the next question. Why did we do that? Because this is a basic u sub. You see something in its derivative. What is the derivative of cosine of 4t? Just forget the minus, forget the square. Just cosine 4t. What is the derivative of that? Negative sine 4t times 4. Do you have that? Kinda, right? I'm off a little bit, but just by a constant. So this conversion allows you to make a basic u sub now that u will be equal to cosine of 4t. And it says it there in those steps. It says right here, I'll scroll up so you can see it. It says, now rewrite the remaining even power of sine using that identity, which was me doing the 1 minus cosine squared. And then it says, let u be cosine x. So it even tells you what the substitution needs to be. So I'm giving you a lot of information right there, right? So now we just carry this out. What's the derivative of this? We just said that's negative 4 sine 4t dt. All right, so I'm using t instead of x. We said we don't have that exactly, right? We have this piece. So Fernando, where's Fernando? What are we going to do now?
We need this is where we scale out.
Scale it out? Okay, how do you want me to scale the left side?
We go 1 over 4.
Okay, negative, right? Because we want to get rid of that negative. So negative 1/4 du is what we will replace sine of 4t dt with. Yeah? Okay, Fernando, let's rewrite the whole integral now. This integral now becomes integral, and then what is this, Fernando?
Is that, I actually don't know what that would be.
Okay, so this is just 1, right? Minus, now what was this? What was cosine of 4t? What did we say that was?
That was the u.
That was u, and then squared. So this is just going to be 1 minus u squared, right? And then this piece right here is this, which is this, right?
Yes.
So negative 1/4 du. And I didn't leave myself enough room up front, so I'm just going to put it here. Does everyone see that? Everyone see that? Okay, that we should be able to handle now because we can pull the negative 1/4 out. We can integrate. Now we're just integrating 1 minus u squared du, which is like the first type of antiderivative we ever did. Those are just basic powers and stuff like that. So let's see. Nicholas? Yes. All right, Nicholas. Okay. Negative 1/4 times. Okay, so you're doing this one? Yeah. How about this one? We're doing antiderivative, right? U, just u, right? Because our variable's u. The antiderivative of 1 is going to be u, not x. And then minus 1/3, u to the third, plus c. There we go, right? And I put the negative 1/4 out front because that's going to have to carry through to both, so I put them in parentheses. Perfect. Last step, just plug u back in. What's u? It's this, right? It's this. So that should be our final answer on the next step. So the antiderivative of this, right? The antiderivative of this is equal to negative 1/4 u, which was cosine 4t. Okay, now I'm going to do this mentally. I'm going to distribute these through. So the next thing should be plus 1/12. And then I have u cubed, which we will write as cosine of 4t with the 3 right there, right? That's how we represent cubing. And then plus c. There it is. So if we differentiate this and like clean things up and cancel and use some identities, we should get back to sine cubed 4t. What do y'all think? Is that okay?
Yeah.
Yeah? So if you have sine to an odd power, you're going to peel off one factor of sine. The even power that's left, you're going to rewrite using Pythagorean identity, and then use cosine, just crank it out, right? So let's do this. I'm going to change the problem. You ready? Let's do that same problem to the 5th power. All right, does anything change with the initial steps? We still factor a sine out, right? And how about this? Can we make this problem just a little bit easier to work? Let's just get rid of the 4. That way we don't have to care about that 4 too much, all right? Okay, so we're still going to factor out one factor of sine. So that will leave me with sine to what power here? Sine to the 4th t times just sine t dt. All right. I feel like I keep calling the same people. But how about James? This is James. This is just James, not the other James. All right, James, so what's different now at this point than the last problem?
I want to kind of take it into 2 sine squared.
Okay, so you see that we have sine to the 4th, right? So because it's sine to the 4th, this identity over here, you are not allowed with this identity to just replace these two numbers with anything you want, okay? Like you can't make that a 4 and that a 4. Like it doesn't work that way, all right? So the best you could do is maybe split it into 2 sine squareds. I'm going to do something a little different. I'm going to do it this way. I'm going to do it sine squared of t, right? But then all of that squared, and then I'm going to have my sine t dt, like that. Which is the same as what James was saying. James was saying, let's do sine squared times sine squared. I'm just writing it a little different than he said it, right? Okay, now at this point, you can use the Pythagorean identity right here in the brackets. So let's make that Pythagorean identity switch. I hate brackets. I don't know why I put brackets, but okay. I'm going to go back to parentheses. That's what sine squared is, right? So that's this, but then we're going to take that and square it. So I need to put a squared out here. And then times sine of t dt. So the only difference right now between the problem that we did before and the problem we're doing now, other than the 4, right? I took that 4 out of there. The only other difference we have is that instead of having this expression just by itself, it's this expression squared, isn't it? Okay. We make the same substitution, right? U here will be what? Cosine of t. And the derivative of that will be negative sine t dt. We don't have negative sine t. We have positive sine t. So we scale both sides by -1. And now we can rewrite. So let's see, Omar's up. Omar, I'm going to go right here, and you can just tell me what you want me to write. I'll put the integral sign for you. All right. What do you want?
So you still get the sine squared?
Sine squared? No, we were here, right? We had taken this, and this is where we made the substitution.
Oh, sorry. 1 minus u squared.
1 minus u squared in parentheses, right?
Squared.
And then all of that squared, you said? Okay. And then sine t dt is going to be, what's that?
Negative.
Negative du. So where do you want? Negative outside?
Yeah.
Okay, negative and then du. We all good with that? Okay, now we have to integrate that. Now in the last problem, because this squared wasn't here, we just did them term by term, right? But the squared's there this time. And so that changes things. You can't just do them individually. What could you do though? Just like expand it out, all right? Like FOIL it out. Okay, so if you came over here and you did 1 minus u squared times itself, 1 minus u squared, then you just do your little, right? So you get like 1 minus 2u squared plus u to the 4th. That's what you would get if you expanded and collected like terms. All right, so that's just a little bit of algebra that we might need to do. But now you don't have that squared anymore. So now you could rewrite this as minus integral 1 minus 2u squared plus u to the 4th du. That makes sense to everyone?
And then put u back.
Antiderivative first. Yep, antiderivative first. So now we go ahead and use our rules for antiderivatives. I'm going to have a negative on the outside. And then I'll put a big parenthesis here. Now we need the antiderivative of these three things, right? So u minus 2/3 u cubed plus 1/5 u to the 5th, and then plus our constant. Now we replace u with cosine. What was it? Was it cosine t? Yeah, cosine t. So I think I'm ready for the final answer. Any questions for the final answer here? All right, here it is. Minus cosine t plus 2/3 cosine cubed t, and then minus 1/5 cosine to the 5th t plus c. I get everything good there? I distributed the negative through to each one, and then I just replaced all the u's with cosine t. There it is. So what happens then if you do something like to the 15th power? You know, then it starts getting really ugly, doesn't it? Because, I mean, if you did that, you would have to do something like sine to the 14th t times sine t dt, something like that. And then you would have to write that as sine squared to the 7th power, which would mean you'd have like 1 minus cosine squared, that's your sine squared, right? But then to the 7th power, and at the end of the day, that's going to wind up being like a 1 minus u squared to the 7th. Then you have to expand that. That's not going to be fun, right? So the reduction formula would be useful here, definitely, right? All right, I would never give anything like that. I just want you to appreciate the fact that, you know, we have to kind of stay in our lane here a little bit. You add some more power to that and it starts getting not reasonable. Agreed? Okay, let's look at the next example. Sine squared x cosine to the 5th x dx. So now we have a mixture of sines and cosines together, don't we?
Yes, sir.
So if we have sines and cosines mixed up, we're still going to start looking at our little cheat sheet at the top here. Let me see, where are our steps here? If we have sine and cosine, then the first thing it asks is, do you have cosine raised to an odd power? Well, we do, right? We have cosine to an odd power. There it is, cosine to the fifth. Well, if we have cosine to the odd power, what you can try and use then is factoring out a single factor of cosine this time instead, rewriting that even power of cosine with the Pythagorean identity cosine squared x equals 1 minus sine squared x, and then making the substitution u is sine x. So it's kind of like the direct opposite of what we just did, isn't it? And then you just kind of hope for the best. So let's try it. So we have cosine to an odd. We will factor out one factor of cosine. I'm just messed up. Let's go get it. Get into it. Cosine x dx. There we go. So we just peeled off one factor of cosine, right? And we need to rewrite the even power of cosine using the Pythagorean identity for cosine squared. Unfortunately, it's cosine to the fourth, which means, like what James did just a second ago, we're going to have to rewrite that cosine to the fourth as cosine squared squared. So let's try that. We're going to have integral, let's see, sine squared x times, I guess I'll do it this way, cosine squared x squared times cosine x dx. So that's where we are. Now the identity. So integral sine squared x, 1 minus sine squared x this time, but that what? Squared. And then cosine x dx. So, I mean, like everything we've done right now is just purely algebra, right? It's just algebra with some identities following this method that's being presented to us, right? Now, what is the substitution that we're supposed to make once we get it all converted over? U is equal to sine x. And this one works out real nice because the derivative of sine of x is cosine x, right? So du is cosine x dx, which we have. Exactly, right? Nothing to tweak, nothing to scale. We're in business. So now we can just rewrite the whole integral. Everywhere we see a sine, we replace it with u. Wherever we see cosine x dx, we replace it with du. Christian? Okay. Christian, tell me what the new integral is with respect to u.
It would be u squared,
Mm-hmm.
parentheses 1 minus u squared, and then squared,
Mm-hmm.
du.
Du. There it is. That's it. That's it. Now we just have, you know, a polynomial basically. If we can expand it all out, we should be fine. We should be able to do them term by term. We'll have to expand this, right? And then after we do that, we'll have to pop an u squared through the whole thing. So I'll just do that on the next line. So here we're going to u squared. If I expand this in my head, you do it on the side, scratch work, whatever. I don't know where you are with that, okay? But I expect everyone could get to that, right? And then you pass your u squared through. And at this point, it's just your general power rule, right, for antiderivatives? No questions there? Everyone happy? Man, the time is just flying by. I mean, for me at least, it's flying by. I know for you it's different. Huh? All right, antiderivative here is 1/3. Okay, I'm going to go ahead and just crank it all out right now. Sine squared x, 1/3, yeah, third. Let me just redo that. 1/3 sine cubed x, and then we're going to have minus 2/5 sine to the 5th x, and then plus 1/7 sine to the 7th x plus some constant. So I went ahead and did the antiderivative of each one of those in terms of u, and then replaced all the u's with sines. Okay, let's take a look at another one. Cosine to the fourth power of beta t. Cosine to the fourth of beta t. Cosine to the fourth of beta t. Now beta is a constant, so beta is like a number. Like it may as well be the number 5, except we just don't know what its value is. So we want to treat it like a constant throughout the whole problem. That's part of why this, remember when we first started talking about integrals, I said that this d thing over here, this differential keeps track of your variable. Because if that wasn't here, you actually would not know if beta is a constant or a variable. You wouldn't know which one's which. Okay, so that tells you, look, t is the variable, beta is therefore a constant. All right, so fourth power. How do we deal with the fourth power? Well, let's go back here. It says if we've got sine and cosine, all right, we've got a cosine. Is cosine to an odd? Nope. Sine to an odd? Nope. Do you have sine or cosine to an even power? Yes. We're going to use the power reducing formulas then. All right? So I'm just going to show you on this one how it works. So I'm going to first realize because this is even, I have to be working with one of these two. Well, I should include that. Okay? So I'm going to first rewrite this as cosine squared beta t, that quantity squared. So that's the same as raising cosine to the fourth, right? But cosine squared beta t can be rewritten using this one right here, right? The bottom one? Okay, so let's be careful on how we use that. I'm going to have something here squared dt, right? So what is it that this becomes? And I told you I don't like this one. I like to use this one right here. So that should become what? 1/2, and then another parenthesis. 1 plus cosine 2. So this formula says whatever your argument is, okay, whatever your argument is, whatever's in the cosine, that thing gets doubled in the formula. You double that expression. So if our expression inside is beta t, we're going to double beta t, so it's going to be 2 beta t. That's what goes here. Understand? All right, now what I'm going to do is just a little more algebra. Remember, this 1/2 is being multiplied here, isn't it? 1/2 times that whole thing in, wait, I'm missing a parenthesis. I am missing a parenthesis. Hold on. Didn't quite give myself enough room there. Yeah, because, no, I'm still missing a damn parenthesis. Okay, so this closes this, and then we have to close this, and then that whole thing's squared. Right? Okay, so when we square this, because this is multiplication, what I can do is I can square the half and I can square the whole thing in here, right? So my next line is going to look like this. Integral, I'll have 1/4 times 1 plus cosine of 2 beta t, and then that thing squared dt. Any questions there? Can the 1/4 come out?
Yes.
Yes. All right. But what we're looking at here, when we pull that 1/4 out, what's left, really, we still are stuck, kind of. I mean, it's, let's see what it is.